Section 2, Objectives. Define and recognize Brønsted-Lowry acids and bases. Define a Lewis acid and a Lewis base. Name the compounds that are acids under Lewis's definition, but are not acids under the Brønsted-Lowry definition. Acid-base theories. We began with Arrhenius's definition of an acid and a base, and in this section we're going to learn two new theories. Each was built upon the previous when they would discover new substances that didn't fit the original definition. So the next one here is some substances that act as acids and bases when they were not in water solutions. And the reason why this is important because Arrhenius's definition requires that the substance be in aqueous solutions, and the definition of acid and bases had to be revised because of that. Now, Brønsted-Lowry acids and bases donate or accept protons, and we'll talk about each of those separately. The Brønsted-Lowry acid is going to be any molecule or ion that donates a proton. It's a proton donor. Now, that might sound a bit strange, but we have already talked a little bit about this before. If you start with a hydrogen atom, which is nothing more than a proton and electron, and if you remove the electron from its electron cloud, all you have left is a proton. So you can see that the H plus is really just a proton. So all acids are defined by Arrhenius's donated protons. We said donated hydrogens to water, but we can think of them also as donating protons to water. And so they are Brønsted-Lowry acids as well. So hydrogen chloride acts as a Brønsted-Lowry when we dissolve it in something else besides water, like ammonia. And HCl is going to transfer a proton to NH3, much as it did when it donated its proton to water. So here is the equation for that reaction between hydrogen chloride and ammonia. And H on the hydrogen chloride is going to go over here and attach to the ammonium and forming an NH3, and over here we'll have an NH4 plus, the ammonium ion. So the proton is transferred from the hydrogen chloride molecule to the ammonium molecule. And the ammonium, NH4, is going to be what's formed in this case. So in the previous example, when HCl was with water, it formed a hydronium ion. So we can see that better if we use electron dot formulas to show how similar these actually two reactions are, even though it produces something a little bit different. So here we have the HCl, chlorine with its 7 electrons and 1 electron from hydrogen. Chlorine now has its octet, its 8 electrons. Hydrogen has its 2. Similar thing over here with water. Oxygen has 6 valence electrons, as you can see from the periodic table. And each hydrogen brings its 1 electron, so now it has 8 electrons altogether. So HCl is going to donate its proton to the water molecule, and it attaches at one of these two places. In our diagram, they just picked this one as a spot to attach it to it, and it didn't bring any electrons, so that the overall ion is going to be positive because it didn't bring any electron to make it neutral. So this is the hydronium ion with a positive charge. We put it in a bracket because it's a polyatomic ion. And what's left is a chloride ion. When hydrogen left, chloride took all its electrons with it, and now it has 1 extra electron that hydrogen left behind. Now, if we look at how HCl combines with ammonia, you can see something similar here. This hydrogen will leave its electron behind and attach to this unshared pair right here, forming an ammonium molecule, NH4 molecule, Again, it didn't bring its electrons, so it leaves this new structure, ammonium, with a positive charge. And again, chloride has a negative charge. So you can see in the top case, it formed a hydronium ion. In this case, it formed an ammonium ion. Now, water itself can act as a Brønsted-Lowry acid. It just kind of depends on what it's with. So if you put water with ammonia, water is going to actually donate a proton to ammonia in a very similar situation like we just looked at. So we're going to have water, but instead of water receiving a proton, it's going to donate a proton to the ammonium to form the ammonia to form an ammonium ion, and water, which is HOH. If one H leaves, then we have an OH left over here. So looking at it from an electron dot notation, one of these hydrogens is going to be left, and it's going to attach to this unshared pair and forms the ammonium molecule, ion, polyatomic ion, with a positive charge. And what was left is this O and this H with all their electrons, and it has an extra electron because hydrogen left it behind. And so that's negative. A Brønsted-Lowry base is kind of like the complement of that, is a molecule or an ion that is a proton acceptor. So if there's a proton donor, there has to be a proton acceptor. And in the reaction between hydrochloric acid and ammonia, the ammonia receives the proton from the hydrochloric acid, and that makes the ammonia actually a base. It makes it a base because it accepted that proton. The Arrhenius hydroxides bases that we've talked about before, such as NaOH, are not strictly speaking Brønsted-Lowry bases. In other words, the whole NaOH is not a base. Only part of it is actually functioning as a base. So it is actually the OH negative ion that's produced in that solution that is the Brønsted-Lowry base. And it's the species that can accept the proton. So in the Brønsted-Lowry acid-base reactions, protons are transferred from one reactant, the acid, they donate, to another reactant, the base, that accepts it. An acid that can donate only one proton, like the example that we've been talking about, hydrochloric acid as our example, it's donating only one proton or one hydrogen ion, however you want to look at it, per molecule, and so we call it a monoprotic acid, one proton acids. And here are some familiar examples that we've had earlier in the chapter. Perchloric acid, hydrochloric acid, nitric acid, each of those has only one H, HClO4, HCl, HNO3. So they're all monoprotic. And so here's an example of HCl donating its one proton to water and forming a hydronium ion. And then here's our chloride ion again. So in this diagram right here, we kind of see on maybe like a molecule level what's actually taking place. So the HCl in this formula right here is donating its proton to water. And as you can look right here, we have a water molecule that ordinarily the water molecules have an oxygen and 2 hydrogens. This one has an oxygen and 3 hydrogens. That's the hydronium ion, as we see right up here. What was left behind was the chloride, and over here is the chloride with a bunch of water molecules surrounding it, and the positive end of the water molecule is attracted to the negative ion. Over here is kind of an introduction to some new things that we'll be covering tomorrow. Is sulfuric acid is a diprotic acid because it has two hydrogens that it can donate, but it doesn't donate them all in one step. It will donate one of the hydrogen ions to the water to form a hydronium. And when it does that, and since it leaves its one electron behind, all that we will have is an HSO4, but it left its electron behind, so it's negative. So this is the, if you remember from your ion sheet down on the bottom left, you have a hydrogen sulfate. Well, that's the hydrogen sulfate. Now, hydrogen sulfate in that same water can also ionize and give off a second hydrogen. That's why we call it diprotic. And it'll form another hydronium ion. And if I take that off, what's left is my sulfate ion. But they have a pretty strong attraction for each other. We've talked about this before. If they have a pretty strong attraction for each other, they will want to recombine. So when the number of these increases, the number of those that are going back starts to increase until finally there are as many ionizing in this direction as those are unionizing back in this direction. So a polyprotic acid is going to be an acid that can donate more than one proton per molecule. So in other words, a diprotic acid is just an example of a polyprotic acid. And sulfuric acid that we had on the previous slide is H2SO4. And then we've also had sulfuric acid earlier, that's H3PO4. So sulfuric acid can donate 2, and phosphoric acid can donate 3. But the ionization of these acids occurs in stages like I showed you on the previous slide. So an acid that loses its hydrogen atoms one at a time actually happens in stages, and each stage becomes more and more difficult to actually occur. And that's the end of this section.